Hi, this is John Whitaker for the Mathematical Analysis 1 course, and this is video lecture number 5. And so what we had left off with was talking about an ordered field, and I want to remind you what that definition was. An ordered field was a field that had an ordering on it, that not only had an ordering but also satisfied two more properties, and that is if x was less than y, then if you add z to both parts of that inequality, it maintained that inequality. And if x was greater than 0 and y was greater than 0, then when you multiply the x and y together, you got something bigger than 0. What I want to do next is make a little bit of an addition to what I said about a field. When we listed the field properties, there were 11 things that we had there. But one thing that I didn't point out was in the definition of a field, there was this number 0 in the field, or this symbol 0, which was the additive identity. And then there was this number 1, or symbol 1, that was multiplicative identity. But in the definition of being a field, 1 has to be different than 0, and we used that 1 was different than 0 in one of the proofs of the properties that we had for fields. So that's something that we have to correct or to add to the definition of a field. All right, I would like to start today in terms of writing things on the board about a proposition about ordered fields. And so here's what we have. It's got 5 parts. We're going to let F be an ordered field. And so here are the parts. 1, if x is greater than 0, then minus x is going to be less than 0. And if x is less than 0, then minus x is going to be greater than 0. So that's 1. Here, we're saying that x, y, and z are elements of the field, ordered field. Okay, so this is x of the field. 2, if x is greater than 0 and y is less than z, then x times y is going to be less than x times z. We already know that. It's like with real numbers. If you take one thing smaller than another and you multiply both sides of the inequality by a positive quantity, x, you don't switch to the inequality, but we're going to prove that. 3, if x is less than 0 and y is less than z, then we do have to switch the inequality when we multiply by x. That is, xy will be greater than xz. Fourthly, if x is different from 0, then x squared is going to be greater than 0, or a positive number. And then, in particular, that says that 1 is greater than 0. Okay? 1 is greater than 0 because 1 is 1 times 1. And 5, if 0 is less than x is less than y, then 0 is less than 1 over y, which is less than 1 over x. Okay, we want to prove these. Here's the proofs. We're going to let x, y, and z be an element of F, which is an ordered field. So first of all, part one, we're going to let x be greater than 0. We want to show that minus x is going to be less than 0. Okay. Well, since x is greater than 0, and remember one of the properties that we have about an ordered field is that if I add the same thing to both sides of this relations, it maintains the relations. So I will do that. I'll have x plus minus x is going to be greater than 0 plus minus x. And x plus minus x is, of course, 0 by the definition of minus x, and that's going to be greater than minus x because 0 plus something is the plus something. So we've shown that part. We also want to show, the second part of part one is we'll suppose x is less than 0. In this case, we want to show that minus x is greater than 0. Okay. And so we do the same thing in terms of adding to this inequality. Since x is less than 0, then x plus minus x will be less than 0 plus minus x. And so that says that 0 will be less than minus x. And that's what we wanted to prove for part one. Okay, for part two, we are going to let x be greater than 0 and y be less than z. We want to show that x times y is less than x times z. And so the way that we can do that is since y is less than z, then that says that z minus y, that's going to be greater than, okay, so this part we take away from y, it's going to be greater than y minus y, which equals to 0. So what we have is z minus y is going to be greater than 0. All right. So x is greater than 0. Okay. So here, what we'll have then is that x times z minus y, that's going to be greater than 0. And the reason that's true is because we're saying f is an ordered field. Remember, if you take two things that are bigger than 0 and multiply them together, you get something bigger than 0, by the definition of ordered field. So that what that tells us, if you distribute here, you have xz minus xy is greater than 0. And then if you add xy to both sides, what you get is that xz is going to be greater than xy. And that's what this says. Just rewriting the statement, xy is the one that's less than xz. So that is part two's proof. For part three, we let x be less than 0 and y be less than z, and we want to show that xy is bigger than xz. That's what we want to show. So we have to switch the inequality here and multiply by a negative. Okay, well, since x was less than 0, then by part 1 of this statement, minus x is going to be greater than 0. Since y is less than z, then z minus y is going to be greater than 0. So we've got these two positive quantities. We're going to multiply them together. And when we do, minus x times z minus y, that's going to be greater than 0. So this is minus xz, and this would be minus or if you will, plus a minus x times a minus y is going to be greater than 0. Now, the minus x times minus y, that's going to be xy. So xy minus xz is going to be greater than 0. So that says that xy is going to be greater than xz. And that's what we wanted to show. So that proves part 3. For part 4, let's don't forget, what we need to show is that we're going to let x be different from 0. We want to show that x squared is greater than 0. Okay, in order to do this, we're going to break it up into cases. So here, since x is different from 0, and f is an ordered set. So when you have two elements of f, they fit into exactly one of the following categories. Either x is bigger than 0, x is equal to 0, or x is less than 0. We know x isn't equal to 0, so we only have two more cases. So we have two cases to consider. So case 1, that's if x is greater than 0, then x times x will be greater than 0, because you're taking a positive quantity and another positive quantity and multiplying together, so you get that greater than 0. So that says that x squared is greater than 0. So this was case 1. I've got to write that down. Case 2 is x if, I should say if before. If x is less than 0, then minus x is going to be greater than 0. So we have minus x times minus x is going to be greater than 0. But minus x times minus x is x times x is going to be greater than 0. And x times x is x squared. So in all possible cases, x squared is greater than 0 when you start off with x being different than 0. Okay, and now we want to consider 1 itself And so what we know is 1 is equal to 1 times 1, since, as I said to begin this lecture, since 1 is different from 0, and 1 is equal to 1 times 1, or 1 squared, okay? That's greater than 0. That tells us 1 has to be greater than 0. And that ends part 4. Now, the last thing we had was part 5, and here we're going to let 0 be less than x be less than y, and we want to show that 0 is less than 1 over y is less than 1 over x. Okay. Well, here's what we'll start off with. Since 0 is less than x, or x is positive, then 1 over x has to be positive. And the reason is that as if 1 over x was, let's say, less than or equal to 0, okay, then we have x times 1 over x will be less than or equal to, here, let me just say this, if it was less than 0 to start off with, okay? Then x times 1 over x will be less than x times 0, and so that would say 1 is less than 0, which we know to be a falsehood. So it cannot be the case that 1 over x is less than 0. Now, the other thing that might happen is 1 over x could be equal to 0. Note, 1 over x cannot be 0, because if it were, then we'd have x times 1 over x would be equal to x times 0. Well, that would be 0. But we know x times 1 over x equals to 1. And 1 and 0 are not the same. Okay? So that tells me that 1 over x has to be greater than 0 if x was positive. And so likewise, that means because y is positive, then 1 over y has to be positive. Let me write that down. So what we have is that 1 over x is greater than 0 and 1 over y is greater than 0, or 0 is less than each one of these. So since x is less than y, and both of these guys are positive, when we multiply them together we get something positive. And so when I multiply 1 over x times 1 over y times both sides of this inequality, we maintain this relationship. So that means 1 over x times 1 over y times x will be less than 1 over x times 1 over y times y. Okay. And here, if you commute these, you have 1 over y times 1 over x times x is going to be less than, here I'm going to reassociate these, this is 1 over x times 1 over y times y. So what we have here, reassociating them, is 1 over y times 1 over x times x is going to be less than 1 over x times 1. Thus, this is 1 times 1 over y, is 1 over y, is less than 1 over x. And we know that 1 over y is greater than 0, So we have that 0 is less than 1 over y, which is less than 1 over x. And that's what we're trying to do. Next thing I want to do is just write up a fact. And that fact is something we won't prove. And here it is. It's a theorem about the real numbers. Here's what it says. There exists an ordered field R, it's the real numbers, which has the least upper bound property moreover, R contains the set of rational numbers, Q, okay, as we call it a subfield, as a subfield, and R is called the set of real numbers. Now the proof of this theorem is in appendix of this chapter 1. So it's in an appendix. Chapter 1 of our text. Rude, but we will not. We'll just understand that R is an ordered field that has the least upper bound property, okay? And it contains the set of rational numbers. We kind of think of R as this smallest set that's an extension of the set of rational numbers that is an ordered field that has the least upper bound property. Well, I want to prove some facts about R. And so the first thing I want to do is have a two-part theorem that we look at. So here, the first part is if X is in R, Y is in R, and X is greater than 0, then there exists a positive integer okay, and really that means a natural number. N is this positive integer, such that n times x is greater than y. Okay. And then part B says if x is in R and y is in R and x is less than y, then there exists a p element of q such that x is less than p is less than q. I want to make comments about what each one of these parts of this theorem are saying. So first of all, this part is really saying that the set of real numbers is not bounded above. You see, you give me any real number, then I can find a positive number. Then I can take a positive number, any positive number you give me, and I can find a natural number, then I multiply that positive number by that, and I get bigger than y. So y isn't an upper bound for the real numbers, no matter what y you give me that is a real number. Unless I can get a real number bigger than that. And it'll have this form. It'll be a positive number times a natural number that I get bigger than that. This second statement, what it's saying is something called density of the rational numbers in the real numbers. And what we mean by dense is that the set of rational numbers are everywhere. And what we mean by everywhere, mathematically, is in R, is that if you give me any two real numbers that aren't the same, one was bigger than the other, then there's going to be a rational number in between them. So there isn't a spot. There are two real numbers such that in between those real numbers there's no rational numbers. Okay? And so in the word dense here, what we're meaning is that the rational numbers are everywhere. Like we hear things like the population density of a city, and if you get a high population density, it means that people are everywhere. Well, here the rational numbers are everywhere. They're between, there's a rational number between any two real numbers you give me that aren't the same. Well, we want to prove those two parts of this theorem. Okay. So here's the proofs. Here's part A. We're going to prove it by contradiction. Okay. And what we do is we assume the given, the first part of the conditions. Let x be element of R, y be a real number, and x be greater than 0. Suppose, the opposite of what we're trying to prove, suppose that for every n element of natural numbers, okay, n times x is going to be less than y, less than or equal to y. Okay. When we look at a certain set, we let A be the set of all n times x forms, where x is a fixed positive number and n is a natural number. So n moves, x we have is fixed. Okay? So the first thing to note is, note A is non-empty. And the reason it's non-empty as x is an element of A. Okay? Because n could be equal to 1, so 1 times x is x, and x is in A. Okay. All right. So here, also, A is bounded above by y. Okay, so all the natural number times x is going to be less than or equal to y. And so
because we're talking about in the real number system, the real number system has the LUV property. So the suit of A exists, and let's give it a name. We call it alpha equals the suit of A, with alpha being a real number. Well, since x is greater than 0, then minus x is less than 0. So what we have is alpha minus x is less than 0 plus alpha, which equals to alpha. So all I'm saying is that the alpha minus x is less than alpha. Okay. Okay. So alpha is the supreme, it's the least upper bound. So if you give me something smaller than it, it's not an upper bound. So alpha minus x is not an upper bound. Okay. And that's by the definition of alpha being the suit. Hence, alpha minus x will be less than m times x for some positive integer m. What am I saying here? I'm saying there's something in A. Here it is, m times x. It's bigger than alpha minus x. Okay? So, what we have is alpha will be less than, okay, look. What we do is we add x to both sides of this inequality. And so, alpha is what we get on this side. On the right-hand side, we'll have mx plus x. Well, that's m plus 1 times x. So, this is a contradiction. Okay? This is a contradiction. This would mean, as this statement would imply, alpha is not the suit of A. And it is. Okay? Now, how come this statement implies that alpha isn't super A? Because this is a guy in A that's bigger than alpha. And so alpha couldn't be a suit. And so what we've assumed is incorrect. So there exists an n element of positive integers, or the natural numbers, such that n times x had to be greater than 1. And that's the proof of part A. Okay, we need to prove part B. So for part B, okay, we're trying to show that Q is dense in R. So we let X be a real number, Y be a real number, and x be less than y. We want to show there exists a P element of Q such that x is less than P is less than Q. Well, here's what we start off with. Since x is less than y, then that says that y minus x is greater than 0. Okay. So that's a positive quantity, y minus x is. And so if you look at the number 1, that's a real number. And by part A of this theorem, there exists, too much steroids, an n element of the natural numbers such that n times y minus x will be greater than 1. So from part A, y is like 1, this is my x, which is a positive number, this is a natural number that I can multiply this positive number by to give me bigger than this real number. Okay. So if we applying A again, part A again, okay, we get positive integers M1 and M2 such that M2 is bigger than, M1 is bigger than NX and M2 is bigger than minus NX. So I'm going to stop there for a second. Look, this is by part A. The NX in this case is playing the role of Y in part A. So it's a real number. And we think of 1 as playing the role of X in part A. And so we're taking, there's some positive integers, some natural numbers, we multiply 1 by to get bigger than NX. And here we're doing the same thing. Minus NX is the Y, 1 is the X for part A, and M2 is something that's going to be bigger than it. Okay? And that's what we have. Okay, now the first thing we should say is that note minus 1 is less than 0. It's because 1 is bigger than 0. So minus 1 times M2 is going to be less than NX, which is going to be less than M1. So that's what we get from the inequalities we had before. We had M1 was bigger than NX. We had minus NX was less than M2. So I multiplied everything by minus 1 on that second inequality. I had to switch the signs. Okay. Now, what I want to say is claim. This is that there exists an M element of the integers such that M minus 1 is less than or equal to NX is less than M. Now look, this makes a lot of sense. We're given a real number, and we're saying there's these integers that kind of sandwich that real number. So you give me a real number, the real number's got to be between an integer and its next one in this way. But really this is based on the fact that Z is an ordered set with the LUV property. And so to prove this, here's what I'm going to do. I'm going to consider the set A equal to the collection of all objects, I'm going to call them T, that are integers such that T is bigger than n times x. So we're just talking about integers that are bigger than n times x. Okay? All right. So we've got this set. Now, this set is bounded below. Okay? And it's bounded below by, if you will, m minus n2. Okay? From our work previously. And since, so I'm saying this fact, but not proving it, since Z, the integers, is an ordered set that satisfies the LUV property. I'm not proving that. Okay. Then the infimum of A, which I'm going to denote by alpha, okay, exists in Z. Instead of calling it alpha, let's call it M, because that's what we're going to use. Okay. Now, it turns out that M has to be an element of A, because if not, okay, then the only way that M isn't an element of A, remember what A was, it was a set of integers that are bigger than n times x. And so M is an integer, but the only way that it isn't in A is that it's got to be less than or equal to. M is less than or equal to nx. In this case, okay, m plus 1 would not be a lower bound of A, because m is the infimum. Okay? And so if you give me something bigger, it's not a lower bound. Okay? Thus, there would exist a T element of A such that we have M is less than or equal to nx, which is less than T, okay, which is less than m plus 1. That's how m plus 1 is a lower bound. There's something in a lower bound of A. There's something in A smaller than n. With, of course, T being an integer, So here, thus, m is less than t is less than m plus 1, with t being an integer. That's impossible. That's a contradiction. Okay. So that's why m had to be an a. And the reason it's a contradiction is in between two consecutive integers, you can't find an integer. So that's because the way the integers are defined. Okay? So if you start with one integer, the next one is 1 plus it. Okay? So there can't be anything between that. Okay? So that means that m had to be, let me reiterate that, had to be an element of A. So what that means is, it's the theme. So that means that m minus 1 is not an element of A. All right? And so that says m minus 1 is less than or equal to nx. So there exists an m element of z such that we have m minus 1 is less than or equal to nx, which is less than m. And that ends the proof of claim. But we're not through with proving that Q is dense in R. Okay. Well, if we think back to some of the inequalities we had, okay, since n times y minus x is greater than 1, we have that ny minus nx is greater than 1, or that ny is going to be greater than 1, or nx plus 1. Well, that's something that's important. So we have, from a previous inequality, remember we had that nx is going to be less than m. Let me write it down here. Okay? And that's going to be less than nx plus 1, which is going to be less than ny. Okay, so this m being less than nx plus 1 comes from the fact that we have, I'll just try to write it right here, that we had that m minus 1 is less than or equal to, so here it should have been less than or equal to, m minus 1 is less than or equal to nx less than m. So if we add 1 to both sides, we have m is less than or equal to nx plus 1 from this part of the inequality I just wrote. Okay? And then we know nx plus 1 is greater than my. So here this says that nx is less than m is less than ny. Now, we can multiply everything by 1 over n, and n was a positive integer, so here's what we have. X is less than m over n, which is less than y. And this, m over n, okay, is a rational number because it's a integer divided by a natural number. So that's what we have. And that is that proof. Kind of a long proof. And it's a good point to stop at. So thank you very much.